Hi, and welcome to College Algebra pre-section 3. This is all about polynomials and special products. We're going to focus on writing polynomials in standard form, add, subtract, and multiply those polynomials. When we multiply them, hopefully we can recognize special products. Otherwise, you have to do it all by hand. And hopefully eventually use some polynomials in applications of problems. I mean, not today, but in the future. So, polynomial of degree n. We call it degree n, where n is the highest exponent. That's what a degree means. The biggest exponent we have that's attached to our variable. If it's in standard form, it should be the first thing right there. Now we want no negative exponents, only integer exponents, so just whole numbers, and real number coefficients. So I should only have, 1, 2, 3, etc., and I should have no imaginaries. Okay. So here, for example, 3x to the fifth plus 2x to the third minus 7x squared plus 11x minus 12. If I look at the exponents, I only have whole numbers. There's no number here. It's implied to be a 1. And this one doesn't even have a variable. So it's what's a constant. It has a variable of 0. Because if we remember, if we treat anything to the power of 0, this equals 1. So it doesn't actually need that. 12 times 1 being, of course, 12. Now, coefficients. Coefficients are numbers in front of expressions with exponents. So 3, 2, in this case, negative 7, 11, and of course, negative 12 will be my coefficients there. So a leading coefficient is the number in front of the variable with the biggest exponent, and a constant has no variable. So as we talked about earlier, without a variable, that's why negative 12 is our constant. Now, again, remember that standard form. We functionally want highest variable to lowest. So when I look at this, what I mean by that is we have functionally 5 x's here. X times x times x times x times x. That's why it's x to the power of 5. And here I have 3, here I have 2, here I only have the 1, and here I have 0 x's. So as I go from left to right, I have less and less variables. The other thing to look out for standard form, if I have multiple variables, we want to sort them alphabetically. So something like x squared y would have 3 variables. It's got 2 x's and a y, and that would go before xy squared, even though this also has 3 variables, because the last remaining thing, x, is more forward alphabetically than the second y. All right. There's a couple ways we can categorize polynomials. 2 things you usually look at. First, what's called the degree. Degree, again, quick reminder, is our highest exponent. So in this case, there is no exponent, so this would be a constant term. It's only 3. Here, I have a degree of 1, so that'd be a linear, which makes sense. It forms that y equals mx plus b structure. Here would be a quadratic to the power of 2. And if you remember from Algebra 2, those form those parabolas. Cubic has a degree of 3. They tend to take the shape of that. And then quartic would be a degree of 4. They also tend to have some parabolic patterns when it comes to end behavior. Sometimes, these tend to be the same, but sometimes the stuff in the middle gets a little messier, so I wouldn't worry about that shape too much. The other way we can do it is the number of terms. So for example, 5 only has 1 term, so it's a monomial. Monomial will be the prefix. Nomial, this root word, means number of terms. So monomial, like monotheistic religion, one God, one term. Binomial, then means two terms, like bicycle's got two wheels. And then, of course, we have trinomial, it's got three terms, like a triangle, three angles. So each one of these things can be described in two different ways. For example, this one right here would be a quadratic trinomial. Both ways would describe that polynomial expression. So operations with polynomials, add and subtraction functions very similarly. We just combine like terms. And by like terms, we want same variable expressions. So here I have 5x cubed and regular x cubed. No number implied there, so it's implied to be a 1. So I get 5x squared plus 1x squared for 6x squared. Move on to the next one. Negative 7x squared plus 2x squared would give me negative 5x squared. And next, I actually have this negative x, and then I also have negative 3 and positive 8 for plus 5. I did it in this way because now I still get my, oh shoot, this should have been a 3 exponent right there. Did it this way because now I'm in standard form, highest exponents, slowly getting down to just my constant. Subtraction functions very similarly. However, we have to take one more step. Anytime we are subtracting an expression, it's often known as distributing this as a negative. So I'm going to flip the polarities of all those expressions. From there, though, everything stays the same. Now I'm just adding anyway what we just did. So 7x to the fourth minus 3x to the fourth gives me 4x to the fourth. We have this positive 3x or x cubed, which we have no other version of. We have negative x squared plus 4x squared, so that sounds like 3x squared. Then we have this negative 4x combined with nothing. And then, of course, we have this plus 2 at the end. So here, this would have a power of 4, so it'd be a quadratic, and it has 1, 2, 3, 4, 5 terms. So probably something like a quinomial or something like that. I wouldn't worry about it too much. Next, we're going to multiply. Multiply is all about the distributive property, sometimes colloquially known as FOIL in a 2x2 system. What I mean by that is I have an A plus B times a C plus D. So FOIL says first terms together, then of course my outside terms, so A and D, my outside things. Then, of course, my inside terms together, B times C. And then, of course, my last terms for each expression, B times D. Okay. So, first, we would multiply our first two terms together, 4x or 2x times 4x, which is right here. And then, of course, we would multiply our outside terms, 2x times negative 5, which is right there. 3 times 4x. And then 3 times negative 5. Well, 2x times 4x would give me 2 times 4, so 8x times x, so 8x squared. 2x times negative 5 would be negative 10x. 3 times 4x would be 12x. And 3 times negative 5 for negative 15. But we have some like terms to combine, so we should. So I get 8x squared, negative 10x plus 12x is 2x minus 15. Here, this is why I don't really love saying foiling, because if I did foiling first, outside, inside, last. We end up not distributing this x. We need to be able to distribute anything, so foiling doesn't work when there's more than two terms in one of the expressions. So let's distribute everything. 2x cubed times x squared would be 2x to the fifth. 2x to the third times 5 would be 10x to the third. And now I'm done distributing the 2x to the cube, so I'm going to move on. X times x squared would give me x cubed. X times 5 would give me 5x. Negative 3 times x squared would give me negative 3x squared. And then negative 3 times 5 would give me negative 15. From there, I'm going to have to go through and find some like terms to combine, like these ones. That looks like it. So we're going to get 2x to the fifth plus 11x to the third minus 3x squared plus 5x minus 15. Last one. We get x squared times 2x cubed, so that's going to be 2x to the fifth. Remember, multiplying with exponents, same base, you just add them. X squared times x, so that's going to give me x to the third. X squared times negative 3x squared. 5 times 2x cubed is going to give me 10x cubed. 5 times x is going to give me 5x. 5 times negative 3 is negative 15. Now, of course, I can just go through and combine like terms. Let's see. We have x cubed and the 10x cubed. Looks like it as well. So 2x to the fifth plus 11x cubed minus 3x squared plus 5x minus 15. Now, interestingly enough, we got the exact same answer up here because all we did was flip the order of the parentheses, which should be able to make sense. Because if I multiply normal numbers, 4 times 5, that's 20. And 5 times 4, that's also 20. So the thing with multiplication is order doesn't matter. These have the commutative property. So even with variable expressions like this, we maintain that commutative property, which is kind of nice. Now, some special properties you might notice. We have, whenever we're multiplying the same thing, but we flip, this is called the difference of squares. A plus b times the quantity of a minus b, we get a squared minus b squared, which if we foiled it all out, you would notice that the middle two terms cancel out. Whenever I'm squaring this thing, remember, please do not distribute the square. That's not okay. You can only do that in a multiplication underneath the parentheses or a division. This is addition, so I have to multiply it out separately, or I have to spread it out separately, and then multiply it from there. Exact same process here. I cannot distribute that exponent. I have to write it out as two different expressions. And difference of cubes and sum of cubes is actually very interesting. So let's try one here. Why would you want to use this form? Well, I'll show you. So let's say I have x plus 3 cubed. If I were to multiply this out by hand, I would have to do x plus 3 times x plus 3 times x plus 3. Well, we don't really talk about multiplying three fractions or three parentheticals together, but I can multiply the first two. X times x is x squared. X times 3 would be 3x. 3 times x would be 3x. And 3 times 3 would be 9. Of course, I can combine those terms together for x squared plus 6x plus 9. Unfortunately, I still have this extra x plus 3 right there, so I'm going to have to multiply that out as well. X squared times x would be x cubed. X squared times 3 would be 3x squared. 6x times x would be 6x squared. 6x times 3 would be 18x. 9 times x would be 9x. 9 times 3 would be 27. So then I can sort of combine some like terms here, and we end up with x cubed plus 9x squared plus 27x plus 27. Now that works out fine and dandy. The thing is, though, that's a lot of multiplications. I multiplied 4 times here and 6 more times here. I combine terms here and I combine terms there. So that is, all sorts of steps you can mess up. However, if I use this formula right here, so this idea that my a cubed plus 3a squared b plus 3ab squared plus b cubed gives me that thing. Now, where do all these things come from? If I'm looking at x plus 3 quantity cubed, whatever is right here in front of the plus sign, that is my a. Whatever is to the right of the plus sign, that's my b. So I'm just going to plug in everywhere I see it. So I'm going to get x cubed plus 3 times x squared times 3 plus 3 times x times 3 squared plus 3 cubed. Oh, terrible, 3. X cubed. 3 times 3 is 9, so 9x squared. 9 squared is 9, 3 squared is 9, excuse me, times 3 is 27. And then 3 cubed, 9 times 3 would be 27 as well. So here, I end up with the exact same answer. One way, if you have the formula, is just a lot faster. Thank you for listening, and I hope you have a wonderful day.